This is Christopher Sernaque hosting episode 14 of season 5 of the Current Topics in Science podcast. This podcast will address breaking scientific news in light of the origins debate and host interviews with scientists. Today we'll be talking with Dr. Winston Ewert about computer models, evolutionary theory, and intelligent design. This podcast is available on the following platforms: iTunes, Stitcher, Google Podcasts, Spotify, and iHeartRadio. Video recordings of the podcast will be uploaded to YouTube. Enjoy the podcast. Today on Current Topics in Science, we have the honor of hosting Dr. Winston Ewert. Dr. Ewert earned his Bachelor of Science degree in Computer Science from Trinity Western University, his Master's degree from Baylor University in Computer Science, and he earned a PhD from Baylor University in Electrical and Computer Engineering. Dr. Winston is the author of 22 technical publications in various journals, symposiums, and conferences, such as the journal Biocomplexity, the 42nd Southeastern Symposium on Systems Theory, University of Texas at Tyler, and the International Conference on Systems, Man, and Cybernetics. Dr. Ewert is a software engineer with various specialties including computer simulations of evolution, specified complexity, information theory, and the common design of genomes. He's also a researcher for the Scientific Theory of Intelligent Design, the Senior Fellow of Discovery Institute's Walter Bradley Center on Natural and Artificial Intelligence, the Senior Research Scientist of the Biological Institute, and Senior Researcher at the Evolutionary Informatics Lab, and a Fellow of the Bradley Center. And now, without further ado, good afternoon, Dr. Ewert. How was your day, and how are you doing?
I'm having a great day, and it's great to be on your podcast.
Thank you, Dr. Ewert. It is a pleasure and honor to have you on Current Topics in Science. And now, since this is Current Topics in Science, let's quickly look at this week's current topic. This is an older article, though. It's from 2019, but I thought it was interesting because it was saying that an evolutionary approach has pragmatic benefits. The article is called Amazon Researchers Say Evolutionary Approach Improves the Selection of AI Models. The article says, Amazon researchers believe there's a better way, namely one involving computational methods that generate tailored architectures. In a paper on the bounds of function approximations presented last week at the International Conference on Artificial Neural Networks, they explore techniques that apply to any computational model, providing the model can compute the same functions a Turing machine can. In this context, a Turing machine refers to a model defining an abstract machine that manipulates symbols according to rules. The paper's immediately applicable result is the identification of genetic algorithms and, more specifically, coevolutionary algorithms whose performance metric depends on their interactions with each other as the most practical way to find an optimal or nearly optimal architecture, wrote Winter. Based on my experience, many researchers have come to the conclusion that coevolutionary algorithms provide the best way to build machine learning systems. But the function approximate framework from my paper helps provide a more secure, theoretical foundation for their intuition. Dr. Ewert, what did you think of this current topic? Do evolutionary algorithms provide the best way to build machine learning systems?
Well, what's actually interesting is that evolutionary algorithms don't really see wide usage. There was a time when evolutionary algorithms were very popular and a lot of people were trying to use them. And there are still some who are very enthusiastic about them. But generally, they've been eclipsed by more sophisticated techniques like deep learning, tree search, large language models, all of these more sophisticated sort of machine learning techniques that we've come up with. And those see a lot of usage, and evolutionary algorithms have kind of fallen by the wayside. And fundamentally, that's because evolutionary algorithms just don't work very well. They're not very good. Other techniques are much more effective. And this case is particularly odd because if you go back and read the paper, it doesn't even talk about evolutionary algorithms or genetic algorithms or coevolution or anything of that sort. The word evolution only appears in the references section in the title of some of the papers that it's citing. So it's really kind of strange that this idea that somehow the paper is saying something about evolutionary algorithms or coevolution. And in fact, the idea that it's saying something about that comes from a blog post the author made, where he asserts that the paper demonstrated something about coevolutionary algorithms, but it just isn't supported by anything at all in the paper. So, no, I don't think evolutionary algorithms provide the best way to machine learning algorithms. I think it's been amply demonstrated that we need to use much more sophisticated techniques. The simplistic techniques, like evolutionary algorithms, just aren't that good. Now, there are some cases where they can be used as part of a broader system, but the big picture is machine learning requires something much more sophisticated than trying to imitate an evolutionary algorithm.
Dr. Ewert, thank you so much for sharing your thoughts on the current topic. And on that note, the origins discussion touches numerous fields of science, so it's unsurprising that computer science is also relevant to this discussion. In his conversation with Dr. Del Tackett, Dr. Paul Nelson was contrasting the power of intellect versus evolution in the development of computers. Dr. Nelson said, biological evolution is driven fundamentally by randomness. In reference to computers, is driven by intellect, by mind, by creative intelligence. Dr. Ewert, may you please expand on Dr. Nelson's quote? Is complex specified coded information exclusively the product of a mind, or can it be generated by randomness?
I think we do need to be a little bit careful in what we mean by that statement. So it's certainly the case you can get sort of seemingly complex specified code with something other than a mind. A good example today is ChatGPT, which has seen a lot of attention, and I'm sure that your viewers are well aware of it at this point in time. You can ask ChatGPT to write you a story or poem or whatever you want, and it will generate a bunch of text, and text is, coded, specified information, and it'll look a lot like what a person would have written if you'd asked them the same question. But there's a couple of important points you got to keep in mind when you think about that. First thing is that ChatGPT is a really sophisticated system. You recall I talked about sort of evolutionary algorithms and how they've sort of fallen out of popularity because other more sophisticated techniques are more powerful. Well, ChatGPT is sort of at the cutting edge using all of the different sophisticated techniques we've figured out how to use. And so at the very least, ChatGPT shows that you really need a highly sophisticated system to produce this kind of coded information. You can't use something real simple like random chance or natural selection to do that kind of thing. But the other thing you have to keep in mind is that ChatGPT didn't just pop out of nowhere, right? It was created by a bunch of engineers, and it's trained on a huge data set of human output. So they went around collecting just a huge amount of humans interacting and following instructions, this sort of thing, and they trained their system based on that. And so if we trace back the source of information, we don't find it originates in ChatGPT. It originates from these engineers and from these humans who wrote all this input. So yeah, ultimately it does trace back to a mind. So when we say that complex specified coded information traces back to a mind, it's important to clarify, we mean it ultimately traces back to a mind. So the approximate source may well be something else, but ultimately, every case where we're able to trace back the source of this information, it does trace back to a mind.
Dr. Ewert, thank you for speaking to the origin of information. That concept is paramount to the origins discussion. In fact, Professor Christophe Adami, a microbiology and molecular genetics and physics and astronomy professor, believes that Darwin's theory of evolution is simple in the sense that it requires only 3 necessary and sufficient components for the process to work: inheritance, variations, and differential survival, sometimes called selection. He continues by saying, evolutionary theory says that only beneficial traits survive in the long run, but it can often be hard to understand how a certain trait might help. This is because of all those trade-offs I mentioned, and sometimes the benefit of a trait only becomes clear after a long time. After all, evolution has had millions of years of trials, failures, and successes. Even 50 years of observation might not reveal to us the long-term consequences of a set of traits and how they interact and play out in a complex world. In evolutionary science, computers, thus, are prediction machines. They answer questions like, What would happen under these rules, given I started in this world, with these starting conditions? Dr. Ewert, what do you think of Professor Adami's statements? Does evolution truly require only 3 working components, and do computers demonstrate the predictive power of evolutionary science?
Well, what's interesting is that Adami isn't even consistent in holding to what he claims here. So he's the author on an important paper called The Evolutionary Origin of Complex Features. And in that paper, they present an evolutionary model which evolves a computer program that performs a particular computation. And they do this by carefully designing the system so that natural selection favors incrementally more complicated calculations until eventually rising at sort of the paramount complicated calculation. And that's kind of weird because they're sort of assuming the point that there's these intermediate stages that can evolve. And they actually knew this because in the paper they wrote that some readers might suggest that we stack the deck by studying the evolution of a complex feature that could be built on simpler functions that were also useful. However, that is precisely what evolutionary theory requires. And indeed, our experiments show that the complex feature never evolved when simpler functions were not rewarded. Now, the same quote also quotes Daniel Dennett, claiming those 3 conditions are sufficient. But here's the thing. You can't have it both ways. Which is it? Does evolution only require having replication, mutation, and selection? Or does evolution also need this assumption about there being incremental steps? He can't have it both ways, which is what he's trying to do. His own research shows that, yes, we need to have more than just these 3 components. And so it's essentially incontrovertible. These 3 components aren't sufficient. Any model of evolution shows that you have to include these additional features and assumptions in order to get a working model of evolution.
Thank you for addressing Professor Adami's ideas. He's one of many scientists studying evolutionary computer models. And regarding those models, a rather famous example is Professor Dawkins's weasel words, where he had a computer simulation generate the words, "Methinks it is like a weasel." Dr. Vicar Komeniko, a mathematician and computer scientist, criticized Dawkins' ideas, saying, "The complexity of living things, however, is sufficiently more complex, irreducibly complex in many instances. Thus, fine changes, such as the substitution of a single amino acid in a protein chain, is unlikely to be rewarded by improved fitness. Improved fitness is only obtained by coarse changes in the overall structure, and often these changes will require moving through less optimal solutions, valleys between the peaks of Mount Improbable. A more realistic genetic algorithm based on coarse acknowledgments shows that Mount Improbable is truly impossible." Dr. Ewert, what do you think of Dr. Komiko's critique of Dawkins, and do you find evolutionary computer simulations to be convincing? Why or why not?
So actually, I don't really like his critique because I think it focuses on what's actually a relatively minor problem, and it misses the bigger problem that the evolutionary process has. So he focuses on this idea of fitness values. The idea being it's very difficult for an evolutionary process to make a complex change if the intermediate versions of that change are deleterious. This has led to a lot of evolutionary theorizing about how evolutionary processes might be able to skirt around the valleys. And they've come up with several ways to get around it, such as appealing to high dimensionality, genotype-phenotype maps, and various kinds of relaxed selection effects. But the real issue isn't actually fitness valleys. Evolution has difficulty crossing a fitness plateau. Even if those intermediate stages of a complex change aren't deleterious, but they're only neutral, evolutionary process is still going to have a really hard time getting across that. See, evolutionary process only works if natural selection is actively pushing in the right direction. It's not sufficient for just not to be pushing against you. It actually needs to be pushing for you in order to actually navigate across a landscape. And so focusing on the fitness values is a bit of a problem because it suggests that evolutionary process could work if only natural selection were not pushing against the change. But that's not sufficient. Natural selection actually has to push towards the complex change. And that's a problem that's way more difficult than that posed by fitness values. And none of the proposed solutions to deal with fitness values are going to resolve what is the big problem. And indeed, if you actually look into the details of all these things, they all rely on this implicit assumption that evolution is going to be able to navigate fitness plateaus. But we know that just isn't true. As for Dawkins' model, Its fundamental flaw is indeed that it assumes every small change which moves closer to the target phrase would be favored by natural selection. And that's pretty unrealistic that every tiny change that made you closer to something would be an increase in fitness. Dawkins himself, in The Blind Watchmaker, where he puts forward that model, is quick to acknowledge it's misleading. Not everyone has been as forthright about this misleadingness as Dawkins was. But ultimately, evolutionary theory, it does rest on an assumption that something like the Dawkins model is approximately true. But everything we know about how to build complex systems suggests that just isn't true. It's not that simple. And Dawkins nor anyone else has ever given any sort of half plausible argument for why we should expect it to be true.
Dr. Ewert, thank you for reviewing Dawkins's model. Indeed, scientific models should be put to the test. And so, let's review the ID model 2. So you had made this prediction. The prediction of irreducible complexity in computer simulations is that such systems will not generally evolve apart from intelligent aid. Dr. Ewert, have you found that the predictions you've made using ID theory for computer simulations have been borne out? And what further predictions have you made using ID theory?
Yeah, so basically, if intelligent design is true, we should be able to predict something about what's going to happen inside an evolutionary simulation. It should give us an insight into what can and can't evolve under what circumstances. And so if we're right about the kinds of limitations evolutionary processes face, that should really be reflected in what happens inside these computer simulations. And so you particularly just quoted me giving a prediction in the realm of irreducible complexity. I imagine your readers are probably familiar with irreducible complexity, but briefly, the idea is you've got a system made up of several parts, and it requires all of those parts in order to function. And Behe's argument was that it's very difficult to evolve such systems. If he's right, we should see evolutionary simulations also fail to evolve irreducibly complex systems. And what I did in that paper, the digital irreducible complexity, was show that that was in fact what we found. We found that you can't manage to evolve irreducibly complex systems for exactly the same reasons that you can't, it's very hard to do in real biological life. Another case where it'd be that under intelligent design, we expect most evolutionary adaptations aren't creating new information. They involve the loss and rearrangement of existing information. And if that's true, well, we should see that in computer simulations. And so in another paper, I looked at a simulation called Sierra, which showed exactly that. A lot of seemingly complex variation showed up in the simulation, but it turned out it was basically all deleting or rearranging portions of their genomes that had all of this complexity result. Another argument that's been developed within the intelligent design umbrella is the idea of the waiting times problem. The idea is that if you sort of look at what would it take to get even a small combination of mutations together, and it turns out it takes an absurdly long time, to the extent that basically the response on the evolutionary side is forced to be, well, you never need more than one mutation at a time. And if this argument is true, well, we should see the same thing happen in computer simulations. So in another paper, I took various commonly used models of evolutionary computation and said, what happens if we run them on a biologically realistic mutation rates? And they all stop working, because it turns out computer simulations use really, really high mutation rates. And if you set them to appropriate levels, they stop being able to solve even these basic problems, toy problems that they use in these simulations. And that's because essentially the waiting times problems prevents them from working whatsoever. And so what we see is these various cases that when we test intelligent design claims about evolutionary limitations in computer simulations, it turns out again and again, that's exactly what we see in those simulations.
Dr. Ewert, thank you very much for explaining how ID computer simulations effectively work. On that note, I was reading your paper, Digital Irreducible Complexity, a survey of irreducible complexity in computer simulations. I found this paragraph where you outlined the ultimate question in this discussion quite important. Here is the full quote. But ultimately, the question is not whether humans can find a way to make it happen. The question is whether Darwinian evolution can involve the system. If Darwinian evolution is capable of developing systems like the Terrian sensory system, then we should see models that demonstrate this evolution. Dr. Ewert, may you please expand on this quote and tell us what barriers are preventing Darwinian evolution from evolving this kind of system? Do you believe that these barriers are insurmountable, and if so, why?
So, to explain a little background, Tierra was an early example of a computer simulation. And one of the later iterations was called Network Tierra, which comprised of many computers talking to each other to create a vast sort of computer simulation of evolution. The creator, someone named Thomas Ray, was explicitly trying to trigger a digital Cambrian explosion. He wanted to see evolution produce this Cambrian explosion. And he didn't get what he wanted. And he actually, at this point, considers the project been a failure, and he's gone off into other kinds of research. What he did was the equivalent of sort of creating a self-replicating cell and letting it loose to evolve in a virtual environment. And when I was looking at irreducibly complex systems in computer simulations, I looked at sort of that design of the original cell that he created and found that there's a system in it which is responsible for sort of looking at the other systems in the network and deciding, which one you might want to migrate to as an organism, and found that it in fact had three parts which were interworking in exactly the kind of way that fit the definition of irreducible complexity. And so I argued, look, we absolutely can have sort of irreducibly complex systems here, but in this case, of course, it's designed. And what that importantly shows is that it's possible for Network Tierra to have irreducibly complex systems in it, but nothing like that evolved. Despite the fact they sort of try to have this vast simulation with all these computers working together for simulation, they didn't get a Cambrian explosion. They didn't even get a single irreducibly complex system out of it. So what stopped it from evolving? Well, fundamentally, the problem's too hard for evolution. The sensory system, it's too complex to arise by chance alone, right? You can't gradually construct it because it needs these three different components. And any partially functional version just doesn't do any good. And it's really unlikely that you could evolve something else and then have that somehow evolve into a sensory system, right? All of the sort of pathways you could imagine to try to get something like this, they're just highly implausible. And that simply reflects what has been argued for some time in the biological realm. Evolution isn't going to be able to account for irreducible complexity, and there just isn't any way around that problem.
Dr. Ewert, in our last question, we had taken a look at whether evolution is capable of creating these sensory systems. In this question, we're going to take a look at the system of our brain, which some have likened to a computer. The Los Angeles Times has an article reporting on the research of evolutionary scientists working to answer the question, can simulating evolution on a computer explain our enormous brains? The article says, next, Gonzalez Ferrero identified 4 challenges that early humans might have faced that could have influenced the size of their brains. They were classified as ecological, me versus nature, cooperative ecological, us versus nature, competition between individuals, you versus me, and competition between groups, us versus them. By fiddling with the levels of each of these factors in the computer model and then running it through many generations, he was able to see which combination of evolutionary pressures was most likely to give rise to the modern human brain size. The results showed that the size of our brains can be best explained primarily as a response to ecological pressures, but not exclusively. Dr. Ewert, what do you think? Can computer simulations demonstrate that the human brain evolved?
So these kind of simulations fall into what I think of as sort of natural selection simulations rather than evolutionary simulations. They aren't really simulating the evolution of the brain. There's nothing in the model which remotely attempts to deal with the complexities of brain evolution. They effectively just assume, well, brain evolution is easy, and just ask, would natural selection have favored bigger brains? And that's just not that interesting of a question from my perspective. They're trying to explore under which circumstances bigger brains would have favored by natural selection. And that's why I think of it as sort of a natural selection simulation, because they're just trying to answer that kind of question. And they don't attempt to model any of the more interesting or difficult aspects of evolutionary processes. And because of that, this kind of simulation doesn't really tell us much of anything about the feasibility of evolutionary processes.
Dr. Ewert, we have now come to our final question. While Discovery Institute is not a Christian ministry and the theory of intelligent design does not require proponents to be Christian, because I know you are a Christian, I ask, how do we love Christ with all of our mind?
Yeah, I think that loving Christ with all our mind means using all of our cognitive faculties for him and his kingdom. God doesn't want us shut up our minds or just a faith or any kind of nonsense like that. God wants us to use our minds to understand him, to understand his world, and to walk out our faith in this world. Sometimes that means working to destroy arguments raised against the knowledge of God. Sometimes it means working hard to understand what God's word teaches. Sometimes it means showing discernment about what you believe on different subjects. Sometimes it just means being wise with how you steward what God has given you. No matter who you are or what you're called to, you can use your mind for the glory of God. And that's what it means to love God with all of your mind.
Dr. Ewert, thank you very much for your time. It was an absolute joy. And to our listeners, thank you for taking the time to learn with us on current topics in science, where scientific discoveries are examined in light of the origins issue. You can find Dr. Ewert's biographical information, his credentials, and written works in the description. You'll also find links to his numerous technical papers, his blog, and a link to the Christ Jesus Ministries merch store. Please share and subscribe to the Current Topics in Science podcast. It's available on iTunes, Stitcher, Google Podcasts, Spotify, and iHeartRadio. Thanks again for listening, and remember, the truth saves.